broadcast is now starting. All attendees are in listen-only mode.
Good morning, everybody. That was Celine Dion. Some people think she may possibly be the best voice, female vocalist in the world. That's possible. There's only one I like better. Her name is Sissel, but Celine Dion is right at the top of the list. So we're going to listen to a couple of her songs today. And today is Thursday. It's November 11th, 9 o'clock in the morning, Central Standard Time. Last week we had Central Daylight Time. And I'm Dr. Minarsik. And, I think we're going to be continuing our discussion on tumors. It's going to be very intense. Last session we had fun. We were rocking and rolling. It was easy. It was fun. This is going to be more complex, more intense. Both you and I are going to have to concentrate possibly a little bit more intensely today than last time. My left contact lens is all screwed up. It was irritating my eye for several days. It was very bad. It was very red. And I had to take it out. And I have to admit to you my big fear for today. My fear is that my eye would be so bad I couldn't do a good job. Now, we also have a lot of complex things to talk about today. I was a little worried about that, but I was more worried about whether I'd be able to see, because when I take the contact lens out, the pain is gone. When I put it in, the irritation can start again pretty intensely, especially nasally or medially. But then at least I could see, especially when I look at my computer screen and see some of the small print. So I guess that's kind of like my excuse for the day. You know, every day I have some kind of excuse, lame excuse as to why I'm not doing great, but we're going to try to do great today. And if you remember, we started out last session with the definition of neoplasia. We started it out at the beginning of the webinar and we reiterated it at the end. So last session, 2 days ago, we said neoplasia, and then we started talking about Willis's definition. You got to keep that in mind, because here that guy is again, Willis. And we talked about this several times. Rupert Willis was a very, very awesome, famous Australian pathologist. He contributed massively to pathology, especially on the cellular level. He's probably almost at the same level as Rudolf Virchow, except he was an Australian. So let's read it again for about the third time and try to understand. Most people have struggled with the understanding of how and why neoplasms occur. And let's listen to Rupert for a second here. Neoplasm, abnormal mass of tissue, the growth of which exceeds and is uncoordinated, that's the key word, with that of the normal tissues, and persists in the same excessive manner after cessation of the stimuli which evoke the change. That's how you can understand neoplasms. And we talked a lot about nomenclature and basic things, and I really had a lot of fun in the last webinar. But now we're going to get into the real nitty-gritty. We're going to get really dirty today. We're going to get really intense. You might even use the word complex, because sometimes this is even complex for me, because we're going to talk about the molecular basis of cancer. And very often this term molecular is used, but like in many aspects of medicine or pathology, when you hear molecular, they're really talking about genetic rather than molecular. So, the molecular basis of cancer. Here are some points. Cancer is caused by non-lethal genetic damage. You know, mutations. And what causes mutations? Well, we all know what causes mutations, the usual suspects. You know, we can give you a list of 1 million things from a one-look dictionary, or I could just narrow it down to 3. Chemicals, physical things like radiation, and viruses and bacteria, or what you call pathogens. These are the usual changes, the usual suspects which cause everything, cause the genetic damage, cause the mutations, which enable growth of tissue to be unregulated. Now, if you remember, you know, from your DNA, you might have a good understanding of how genes code for proteins, enzymes, structural proteins, and they do this and this. But then you have to remember there's a whole bunch of genetic information on those chromosomes that don't really make exactly directly, you know, enzymes or proteins. They're called regulatory genes. Yes, I agree. In some parts of their regulation, you know, they make proteins and they make enzymes. But the regulatory, the growth regulatory genes are mutated. They have genetic damage, damage that cannot be fixed. Or perhaps it could be, but the spell checker or DNA repair genes, you know, could be mutated. There's a whole wide family of genetic things that could go wrong at multiple levels. And we're going to talk about most of them, most of the common regular ones. So let's talk about the so-called growth regulatory genes. Some people call them tumor regulatory genes, and that may not be exactly wrong, because in the process of the tissues being non-regulated because of these mutations here, you may be developing a tumor. But in almost every case, the normal regulation. What does regulation mean? It means inhibition. When you regulate something, you inhibit it. You know, you're going down a highway at an excessive speed, and a cop stops you. He's regulating you. He's not telling you to go faster. He's telling you to slow down. He's inhibiting you. So here is a general scheme in which we're going to also expand on each one of the so-called normal regulatory genes. Well, those are the proto-oncogenes. These are the genes that are mutated. These are normal genes. But when proto-oncogenes are mutated, they become oncogenes. Okay? Now, oncogenes do what any gene does. It makes things, okay? It regulates things. So the product of an oncogene could be oncoproteins, okay? And these proteins are not normal, but the end result of which they lose their growth regulatory powers. We already mentioned the DNA repair genes. Whenever you have a mutation in a gene, and it's not good technically, if it is single-stranded DNA, not double-stranded, okay, you can repair it by a group of genes which are called DNA repair genes. They're like a spell checker, okay? They repair damaged or mutated DNA, which ultimately could give rise to neoplasms. So you have mutations of these, and bingo, you got some more reasons for development of tumors, benign and malignant. There is a whole family of genes we talked about several webinars ago called apoptosis genes. We talked about the apoptosis cascade, the sequence of events that happens when a cell, it's time for a cell. Somebody decides it's time for a cell to go to cell heaven. Okay, so there's a sequence of changes that happens both genetically as well as visually, okay? Just like dysplasia. The sequence, and this is called apoptosis. But let me ask you this. What happens if the genes that regulate apoptosis are mutated, or they become oncogenes? Then you don't get apoptosis. The cells don't die. And when a cell doesn't die, it proliferates, okay? Are you starting to see the picture here? Now, just like we talked about coagulation, inflammation, healing, this is all a multi-step process. We talked about dysplasia. Last webinar, we showed you cells in which the nuclei became bigger and darker and bumpier, you know, as a multi-step process. Well, while you're looking at those cells, having all those changes, there's also a sequence or a multi-step procession of events which are causing those changes. Okay, so we're going to talk about the transformation. And what is transformation? Transformation is a malignant transformation. Transformation is the process, the multi-step process by which normal cells become tumor cells. And progression. Now, I'd like you to remember these two words because these are going to be coming up over and over again. You have to have something that causes the mutations. That's the transformer, okay? That is the carcinogen, okay? That's the initiator. And then you have something called progression. which is the promotion, the multiplication of cells, the growth of cells, okay? So in this process, and this is more or less a sort of a linear step-by-step thing. It's not exactly, but even if it is or it isn't, these are all of the factors that happen in the process of transformation of cells into tumor cells. First of all, they have to be self-sufficient in growth inhibition signals. In other words, they have to lose their signals which inhibit their growth, and they're insensitive to growth inhibiting signals. Now, think about it. Don't think that a cell receives some kind of message which tells it to go wild. No, that's the way stupid people think about it. A cell, in the process of its normal growth, gets inhibited by the substances which would inhibit it. So what happens when you inhibit an inhibitor? It's like a double negative. When you have inhibition to inhibiting, that means it's like promotion or transformation. That's part of it. Apoptosis is something we discussed. Every cell has to die. Every person has to die. There's a multi-step orderly process for that. And if that cell evades it, because the process of apoptosis for those cells is inhibited because the genes that control it are mutated, that's another factor in malignant transformation. Now, in order to have a mutation, you need to have a change in the DNA. If the DNA cannot be corrected, okay, in defective DNA, we'll call that a mutation, okay? But if that can't be checked by the mechanisms which repair DNA or DNA repair genes, there's a whole multi-family of those as well, then that abnormal DNA persists, doesn't it? Because it's not repaired. Finally, oh no, not finally, but if you remember, when we talked about chromosome anatomy, we saw, of course, the centromere, but we didn't talk too much about the telomeres. Centromeres are in the middle of the chromosome pair. Telomeres are at the very end of the chromosome. And those telomeres are structures which determine or limit the number of mitotic divisions that a cell can have. So let me ask you this. If your replicative potential is checked by telomeres, but you have an enzyme produced by defective genes, oncogenes, called telomerase, then the telomeres aren't going to work, and that cell will no longer have a limit to the number of mitoses. You cannot have any tumor larger than about 1 millimeter or 2 unless it has a blood supply. So let's say there are genes which appear, which enable a small theoretical clone of cells to grow simply because it brings in blood vessels. Just like when we talked about healing and repair, okay? You have angiogenesis in tumors if they want to grow more than just a couple millimeters. They have to have the capacity to invade. That's also a multi-step process. And most malignant tumors have the capacity, which they may or may not exercise, to metastasize. And that's really a complex process. It's not just boom, one cell goes from one area to another. You have to have things that enable it to loosen up from the group, to invade, to destroy a basement membrane, to invade the blood wall of the blood vessels, to go downstream, to then invade the wall of the blood vessel again, set up another clone, and do its growth by the things, all the factors we talked about before. I'm going to show you this. I generally don't like things like this, but I really love this one. So let's drop this down. and pop this up. And it's very logical, okay? Even though it has a lot of blocks. You have a normal cell. If there's DNA damage, you have DNA repair genes. But what if those genes are defective, mutated, okay? That's part of the process. Or they could be inherited as well, okay? Or they could be mutated by virtue of being acquired mutations. Okay, so now you have mutations in the genome of groups of cells, okay? They could be activated further by growth-promoting oncogenes, a whole wide variety of different things, or they could be inactivated by tumor suppressor genes, which are really growth suppressor genes, okay? So if you suppress the suppressor genes, you have now unregulated cell proliferation. If those cells normally would die, apoptosis, so to speak, but you have defects in the genes that regulate apoptosis, now you have decreased apoptosis. So those are two bad things to happen, because now these two factors come in to form a clonal expression, okay, ultimately starting from one cell, theoretically. There's processes by which angiogenesis promotes that to make it grow bigger. There are processes by which the normal immune recognition of those new cells are interfered with, which we'll talk about. There could be even additional mutations to this clone where they could differentiate, or they could die, or they could become worse. Tumor progresses. Technically, you have a malignant neoplasm which invades by definition. If it's malignant, it's invasive. And the metastatic sequence, which we're going to talk about as well. Okay, that's kind of a heavy thing to throw at. I told you today it was going to be a little bit intense, and both of us have to concentrate more than usual. Let's take the normal cell cycle again, okay? You have G1F, the new cell, has all of these pre-synthetic things happening to it. Finally, it synthesizes DNA, okay? Then after it synthesizes DNA, you call this post-synthetic, or G2, or pre-mitotic. Well, all these little different figures have regulations that go from one step to another, okay? And the enzymes which regulate the transitions are called kinases. And if you remember, kinases are enzymes that put phosphate onto chemical, okay? Now, let me ask you one thing. Wouldn't you say in this complex scheme of events, we have something called regulation, okay? Because in order for one step to go to another step, you have to have a sentinel or a check to see whether it's ready to go. What happens if the genes which control the sentinel that's at the gate for changes are interfered with, okay, due to mutations? That's probably not the very best example, but we're going to see many, many more examples of inhibitors being inhibited. I guess that's probably a best way to define cancer. The inhibitors to growth regulation, of which there are many, are inhibited. So an oncogene is a mutation of a normal gene. The normal genes are called proto-oncogenes. They're mutated to become oncogenes. What happens if you have a mutation in a growth factor gene, okay, which gives rise to growth factors? Well, the growth factors now are mutated in such a way that they may not be regulated. Not just the growth factors, but growth factor receptors as well. We're going to see 4 examples of this, and they're not intended to be memorized, or the so-called concept of signal transduction proteins. What if the signals, okay, which determine the growth are now mutated, okay? So the RAS gene, coding for RAS proteins, is mutated, and it's normally inhibitor or a regulator, and bingo, that regulation concept is now lost. The policeman has just lost his gun and his badge. He can't regulate you anymore, okay? Or the so-called nuclear regulatory proteins, not just the DNA, but the proteins, the histones. In a way, they regulate the DNA, don't they? They encapsulate them. They keep them coiled up nicely. But what if there are genes in which they lose their regulatory properties? Okay, then you have expression or non-inhibition of the DNA, or these so-called cell cycle regulators, which we just saw an example of in the previous one. Whoops, I'm sorry about that. Where were we? Dum. Let's see, where were we? Well, here's where we are now, and here's where we were before. Here's are your cell cycle regulators. If they lose their regulatory properties by being inhibited, oncogenes, bingo. You now have loss of regulation of the normally very tightly regulated cell cycle. So, can an oncogene, besides act on the growth process to inhibit the inhibitors, can it also make proteins that do that job? Of course. So generally an oncogene codes for an oncoprotein because the gene doesn't act all by itself. So here's going to be 4 examples now. It looks like we're going to have a lot of information here. It's not intended to be memorized. It's intended to be understood. Here's a bunch of growth factors that we talked about a few webinars ago. Okay, like a hepatocyte growth factor, a transforming growth factor alpha, INT2, which is a fibroblast growth factor, or platelet-derived growth factors. Okay, they may not be exactly doing what their name would suggest, but in that case, they are normal genes. In other words, they are proto-oncogenes. In the process of the mutation, they then become mutated to either overexpress or amplify. Now, there is a little bit of difference. You might think they're very similar, but just to make things clear, an overexpression means that there is a switching on of genes in cells in which they normally don't switch on. So like, for example, older cells or more differentiated cells, basically certain genes are switched off. That's the whole process of differentiation, isn't it? But let's say that they are not switched off, or they occur when they shouldn't occur. That's overexpression. Now, amplification is simply an increase in the number of copies of a gene sequence. You increase the number of copies, you generally activate it, increase its activity. And these are various tumors, malignant tumors, like, the brain cancer, astrocytoma, bone cancer, stomach cancer, bladder, breast, melanoma, in which there have been found that this mutation actually occurs. Now, if you remember or memorize these exact things and trace them back to the exact growth factor, you're doing a lot better than I can, because I haven't been able to do it in 12 years. Here's another example of growth factor receptors being mutated. And these are the normal proto-oncogenes coding for the proteins which comprise the growth factor receptor. And once again, if those genes are overexpressed, or amplified, or perhaps even traced down to a single point mutation, okay, they now become, lose their ability to regulate. And here are some of the tumors that occur because of that. Now, I want to warn you, this slide is at least 5 or 6 years old. I can promise you that if there was 1 or 2 things on the basis of a certain receptor, it's very possible, like the growth factors in general, besides leukemia or besides a glioma or besides a breast cancer. There might have been others. And don't forget, certain cancers like breast cancers, it's not just one EGF receptor, for example, that is mutated, the gene that codes for an EGF receptor. It could be other mutations at other levels as well. Here's the third example, so-called signal transduction proteins. Okay, a signal transduction is I'll read it from the bottom. It's a process by which a physical signal is transmitted through a cell. That's why it's called transduction. A series of molecular events, usually by kinases, okay? Enzymes would put phosphate groups onto things and ultimately results in a cellular response. Okay, so there's a signal going through a cell that causes it to respond in a certain way. Now, the proto-oncogenes, the normal genes, the largest group of these are the RAS proteins or the RAS genes. There's KRAS, HRAS, NRAS. There's another one called ABL, okay? Probably the single most important studied one as well. Another one called BRAF, beta-catenin, okay? By a point mutation or a chromosome translation, these proto-oncogenes are muted to become oncogenes, the ultimate result of which could be expressed in various specific types of malignancies. Okay, we're going to spend a lot of time talking about this one a little bit later, the so-called non-receptor tyrosine kinase, because it had the knowledge of it and the way to deal with it has resulted in a cure. Did you hear that? Me say that? Cure, C-U-R-E, almost a cure of a very, very common malignancy. Actually, somebody in my family has it, okay? Nuclear regulatory proteins, again, you could imagine what they do. They're transcription factors which regulate the passage transcription from DNA to messenger RNA. And these are the so-called Mike genes, the normal genes, which by process of either amplification or translocation result in a wide variety of common malignancies. Okay, now you may have been told that the Burkitt lymphoma is caused by the EB virus, if you want to think very, very simplistically. But if you look into the molecular mechanisms which happen, ultimately resulting in that malignant lymphoma, we have a proto-oncogene due to a translation or translocation on a chromosome, resulting in loss of regulation again. Or could we say inhibiting the inhibitor? And another thing about this very, very important common MYC, or I call it Mike gene, is that it's also involved, besides dealing with transcription factors, also involved with apoptosis. So, and there are other genes that interfere with apoptosis. And remember, if you interfere with apoptosis, you're going to interfere with that cell's normal process to die. And if the cell doesn't die, it grows. And don't you think that would be a neoplasm factor if a cell keeps growing rather than dying? Okay, here are the two most important and widely studied genes. P53, this is probably the earliest one. It was discovered in colon cancer, but actually a P53 mutation is now present in more than half of all human cancers. And a RAS mutation, whether it's H, N, or K, is present in about 1/3 of all human cancers. So these are huge biggies, okay? And probably every day there's a new malignancy which can be ultimately traced to a P53 or a RAS mutation. P53 is a gene which codes for the process of the G1 to S transition. Remember, in the cell cycle, you go from pre-synthetic to synthetic, and you have a sentinel. Well, let me ask you this. If there's a mutation and the sentinel is taken out, he's shot, in the watchtower, he can't do his job. And now that's a process of transition of the cell is hastened. It can't be regulated. It can't be stopped. It's also involved in apoptosis as well. And if you ever hear, I think you should know exactly what P53 does, even if you forget most of the others. And probably RAS as well. It's probably in fact, it is the single most common abnormality of oncogenes in human tumors, okay? It's present in about 1/3 here. This one's mutated in about half of cancers. You know somebody that has cancer, they probably have a P53 or RAS mutation. Here's a RAS protein in case some of you out there are biochemistry jocks and you wanted to see a little bit more. This is a list, once again, not intended to be memorized. Why? Because I can't memorize it. So you don't have to either. These are genes. For example, the gene that codes for transforming growth factor beta. Remember, a growth factor? Well, if it is called a suppressor gene, that means it regulates, it suppresses the growth. So if it's mutated, it doesn't suppress the growth. So a TGF-beta mutation could ultimately be expressed commonly as a colon cancer, but there are others. So let's use that example for all of these different genes, okay? These so-called growth suppressor genes. Now remember, in the literature, they often call them tumor suppressor genes, but they're really growth suppressor genes, aren't they? Because if these genes are suppressed, they can no longer regulate growth. Okay, and it's a factor in malignant transformation. E-cadherin in stomach cancer. NF1 and 2, you remember we talked about the familial disease neurofibromatosis 1 and 2. Well, this a gene as well. Ultimately, these suppressor genes, if they're suppressed, they might give rise to neural tumors. APC, okay, beta-cadherin, adenomatous polyposis coli, okay, so that could be a GI malignancy or a malignant melanoma. SMADs, more GI cancers. Retinoblastoma, nice and brilliantly called RB gene, growth suppressor genes, mutated retinoblastoma. P53 we talked about practically in at least half of all human malignancies. Wilms tumor, okay, the WT1, that's a gene which when suppressed cannot regulate growth. In this case, it winds up being a tumor in which the kidney is the primary area. P16 or INK4A, commonly GI or breast. We have also seen that if there is a familial type of malignant melanoma, this gene will also be involved. Very easy to understand, BRCA, breast cancer, both 1 and 2. A suppressor gene, which when mutated to become an oncogene, develops breast cancer. And there's a wide variety of genes in prostate, the most common malignancy in men, but there's a gene called KLF6, which once again follows the same principle of a suppressor gene being suppressed or mutated, and therefore contributing to the further unregulated growth of tissues. Okay. Just out of curiosity, I'm not going to go into the things, but we talked about P53 being involved with suppressing apoptosis or evasion of apoptosis. We talked about MYC as being one of those two. So when we talk about the concept of evasion of apoptosis in general, once again, it's not one single gene. It could be a combination of genes working together, or even working individually sometimes. DNA repair gene defects. Okay, I have 6 diseases here which can be attributed to DNA repair defects. Okay, so remember, these are not necessarily malignancies in themselves, but they are diseases in which the patient has a difficult time or problems with proper repair of damaged DNA. So DNA is like a spell checker, okay? It makes sure after you type your book report that you have correct spelling and commas and stuff like that. So one of the most common types of colon cancer could be an inherited type or familial type of colon cancer that is not polyposis. It's called HNPCC, hereditary non-polyposis cancer. It's also called Lynch syndrome more commonly, okay? So in that case, we have DNA repair gene defects, but we may also have problems with these genes as well. Xeroderma pigmentosum, okay? It's a gene which ultimately is involved in ultraviolet light. Here's somebody which has damaged skin because of it. But remember, this person also has damaged DNA repair genes as well. Similarly, another type of disease called ataxia telangiectasia. Ataxia means they're going to have problems in balance or cerebellar coordination. Here's your telangiectasia or dilated vessels. And you would think that maybe this person may also be more susceptible to neoplasms because the genetic mutations which occur cannot be fixed. Okay. Bloom syndrome. Okay. In this case, there's a mutation in the gene that codes for helicase. This is a classical patient presentation. I'm not going to go into it. I have written down at the bottom here a little bit of a description of each one. But in Bloom syndrome, also increases cancer susceptibility by making defective helicase. And if you think helicase works to break down the DNA helix, now you can understand why this thing could result in this patient could be more susceptible to malignancies as well. Fanconi's anemia, it's a type of anemia that's also closely linked in with leukemias, and it's also a type of anemia in which is called an aplastic anemia. It's the most common type of inherited aplastic anemia. Most aplastic anemias in which you see no marrow, okay, it's aplastic, might be due to the fact, whatever the connection is, the patients with inherited forms of this type of aplastic anemia would also be much more susceptible to malignancies of the marrow or acute leukemias. Okay, let's keep rolling. This is kind of intense, I'll agree. I don't know, I'm not going to ask you a question. I'm not going to take a survey. But if you were here for the last webinar when we talked about cancer, in my opinion, everything was fun and flowing easy and telling stories, a lot of personal type anecdotes. But this one is a lot more intense. This is very, I would even use the word complex. I had to be much more careful in preparing for this one. Well, you guys all know what this is, don't you? If you smoke, or even if you don't smoke, you know this is a book of matches. Did you ever count the number of matches in the book of matches? There's 20. It looks like about half of them are gone, which means after all of these matches are used up, you can't light anything anymore. Okay? So if a cell divides 20 times, we're not going to say 20, but it's a limited number, it can't multiply after that. That's what a telomere does at the end of the chromosome. It limits the number of mitoses a cell can do before it's ready for the apoptosis farm, okay? Generally speaking. It's like a cat having 9 lives. After your cat runs across the street 9 times and doesn't get hit, okay, there's no more guarantees that it's not going to be alive after the 10th running across the street. If a telomerase is present, it is present in most of cancer, most of human cancers, we now lose the number of mitotic divisions that a cell can have. So now it has unlimited replicative potential. Isn't that one of the features of malignancy? Unlimited replicative potential, because its telomere has been damaged by telomerase. Okay? And what about tumor angiogenesis? Think about it. You could have the worst malignancy ever imagined, okay? But if that group of cells cannot be nourished by blood vessels, it'll never kill you. It'll never get bigger than a piece of rice, okay? So you have to be within a 1 or 2 millimeter of a blood vessel for tumors or anything to grow, because it needs oxygen. Tumor cells need oxygen. Tumor cells need sugar, okay? So how do we get tumors to grow big? In the process of malignant progression, there could be activation of VEGF, or vascular endothelial growth factor. Remember, I told you it's probably the most important growth factor, or fibroblast growth factor B. And even though it's called FGF, it basically works on things other than fibroblasts as well. It's not specific for fibroblasts. Now, let's do another example here. Take anything in your body. Take your arm, take your pancreas. Why is it as big or shaped like it is? It can only be as big or as shaped by virtue of the blood vessels that feed it. So that's also true with tumors. A tumor size is regulated not only in weight or total size, but also in shape, simply by all of the factors which feed it blood vessels being in a kind of homeostasis with the anti-angiogenic factors. And all of these are not simple one-step processes either, are they? You would expect that. So regulation for tumor growth would mean that the angiogenic factors are outweighing, they're tipping the scale over the anti-angiogenesis and the angiogenesis factors. Okay, I'm going to show you this picture here, and maybe we'll take our break afterwards. I don't know. This is one of my favorite diagrams, and you might think it's complex because there's a lot of stuff, but it's really one of the few things that kind of takes the whole picture in almost a linear fashion, like all the sequences we saw with inflammation and whatnot healing. They were in many respects linear. So at the top, we have this thing called transformation. That's the beginning of this saga or this sequence. Transformation being the process which we have just outlined in many ways by which normal cells become malignant cells. We talked about some of the growth factors, okay? We talked about angiogenesis, okay? We talked about the fact that in the process of growth and separation from each other and adhering and in destroying the limitations of the cells, for example, a basement membrane, it then destroys or invades or infiltrates, gets bigger by virtue of angiogenesis. Technically then, not only did it invade that basement membrane, not only did it invade the extracellular, we'll say the tissue under the basement membrane, be it connective tissue or whatever, but now it has the ability to invade the wall of a blood vessel or the wall of a lymphatic, which is very, very thin. Usually lymphatic vessels are no more than one endothelial cell thick, hardly at all. Then, of course, once it's inside the vessel, it takes a free ride by the process of embolization, like blood clots do. It then still has the ability to not only adhere to the wall again, but to invade it again or undergo extravasation. Now you're in a completely new area, 20 miles downstream, and you have something called a metastasis. Here, let me make this a little bit bigger. Okay, this is the process by which you have a transformed cell now being malignant, okay, invading a basement membrane, loosening up from the cells, invading through the basement membrane, going into underlying tissues, invading the wall of a blood vessel, also at the same time perhaps being fed by blood vessels to make it grow, embolizing, okay, sometimes it's coated with platelets as it's going downstream, adhering again to the wall, just like it had to adhere to the wall here, and now extravasating, getting fed by some more blood. That is basically a visual, a beautiful, graphic, diagrammatic picture of what goes on with cancer. In this case, we're talking about epithelial cancers or carcinomas primarily. Okay, let's see if we want to go on a little bit more. We want to stop. Okay, we'll take two more comments, and then we'll take our music break, because we've said a lot, and it'll probably get a little bit easier after this. But we use this word invasion or infiltration. You know, what does that actually mean? Well, we have known forever, even before we knew about genes, is that tumor cells basically lose their connections to each other when they're malignant. Here, let me make that a little bit better phrased. Normal cells, like in the skin, are connected to each other by a whole wide variety of things called cellular adhesion molecules, or desmosomes, whatever you want to call them. But when they become malignant, they lose that ability to stick to each other. So tumor cells don't stick to each other. But they could then attach to matrix components, okay, which is non-cellular, or just as though they lost their connections with neighboring cells, they now develop connections with matrix components, which normally they wouldn't have. In the case of a epithelial invasion, you could take skin, but you could take any carcinoma. They can now have the ability to degrade. Not only have they connected to your matrix, but they can degrade it. There could be activation of collagenase. And oh my God, that's probably the last thing you want, because now this enzyme, which dissolves or degrades or breaks up collagen, is now helping the tumor cells to invade. Okay, and of course, once it invades, by virtue of growth and other factors, you have migration. That's how tumors get bigger. It's not just because they are given blood supply or they have the ability to dissolve the stuff around it. they can actually migrate as well. Remember some of the growth factors that we talked about earlier were actually involved in migration of cells, motility. So here we go. Here's a diagram of what we just said. These are cells which are connected to type 4 collagen, which is most basement membranes. But they loosen up their connections to each other. And as they loosen up their connections to each other, they attach more densely to the basement membrane. But don't forget, if they have collagen, they can also degrade it as well. Now we have degradation of the basement membrane. And once that basement membrane is degraded, it makes it easier for the cell using something called motility, okay, to spread or infiltrate. So when you have been told already by me 10 times that the number one thing that differentiates malignancies from non-malignancies is invasiveness or infiltration, you are now seeing that word invasiveness in 4 easy steps. Okay, you know what? We could take a break here, I guess. And I'm not going to go into this, but no, let's talk about this after the break. So let's drop this guy down over here. And let's put you back onto our nice little view of the wall, which is going to be over here. And we'll hear 3 songs, and I think at least 1 or 2 of them are going to be by that awesome singer, Celine Dion again. See you in about 10 minutes, folks. Wow. I really needed that music break. Here, let me tell you something. I flashed this word intense. You know, every year when we do the discussion on cancer, it's very long. And parts of it are like really fun. Like the entire last session we did on it, in my opinion, we were really rocking and rolling. It was like really fun, really smooth, really easy. The second half now, which was today, and we did the first part of the second half. It's very, very intense. It could be very, very complex. I have always the great fear of two things. Number one, I don't understand it perfectly easily myself, but even more of a fear is that I might have a hard time explaining it to you. So sometimes when I think back of the whole session, I'll think, well, I think we did okay today, but it was very, very intense. Even though it seems like most of the time we were talking like aliens, you know, talking about concepts which may have been completely unfamiliar to you. But I think, and I know that now the second half of this presentation today will be not exactly as much rock and roll fun as we did yesterday, but it'll be, let me use the word, easier, even if you didn't think it was easy so far. So here we go. Let's pop up the PowerPoints again and just mention in passing, without going into a lot of fancy arrows and diagrams, the genes which are often indicted as being mutated when patients have metastases are NM23, KAI1, and KISS. So wouldn't it be really, really nice if we could have a better understanding of these genes, know how to regulate them or prevent them from being mutated or whatever? Wouldn't it be really, really nice if every person that had cancer, we can control or suppress their metastases? That would probably be the single best thing. You know, a lot of people say to me, and probably to you, why can't we cure cancer? Well, I think after what we talked about today, you see that there are so many factors and so many cancers. That question is basically meaningless. Why can't we cure cancer? We could act, but if we could act on these genes, it would be phenomenal, wouldn't it? Let's talk about some of the chromosome changes involved are associated with cancers. The most common type of chromosomal problem is a translocation, where a part of one chromosome gets switched with another part, okay? But also an inversion, where a certain portion of a chromosome, and here we have the Q, being reversed, okay, which could happen, as well as a bunch of other things. But these are the two most common types of chromosomal rearrangements that are involved in cancers. And also remember, in general, most of your so-called hematopoietic malignancies like lymphomas and leukemias, most of them can have can be traced back to either some type of chromosomal rearrangement. In fact, very, very often, in order to properly diagnose a certain type of leukemia or lymphoma, you have to understand where the translocation or inversion was. And now that we have a greater knowledge of chromosomal anatomy and genetic probes and stuff like that, we can also see an increasing number of chromosomal problems, not just in the hematopoietic malignancies like lymphomas and leukemias, but the regular non-hematologic malignancies, the carcinomas, the sarcomas, okay? Here's a list of the common ones. The one at the top is the one I think you should really, really know well, because it has been classically the most spectacular. And look at, most of these are lymphomas and leukemias, aren't they? Even this word sarcoma is often regarded as being present very often in bone marrow, okay? But chronic myeloid leukemia, which we said was a chronic type of leukemia, it's not an acute leukemia, but it classically always had something that we knew was funny in its chromosome. We called it the Philadelphia chromosome. We know specifically now, if you look at the way they label these things, that it is a crossing between chromosome number 9 and chromosome number 22 in Q, which is the long arm of chromosome 9, with Q, the long arm of chromosome 22. So that's a classical translocation. And in the result of doing that, it alters or, in a way, creates certain genes. And of course, these genes could be more disastrous in the development of a malignancy than the translocation itself. So, astoundingly, we have medicine, we have tyrosine kinase inhibitors now, which can affect it at this stage. And as a result, the mortality from chronic myeloid leukemia going into acute leukemia and often being fatal has been amazingly improved. Okay? A lot of the acute leukemias, acute myelogenous leukemia, acute lymphocytic leukemia, have often predictable translocations as well. Burkitt lymphoma, okay, mantle cell lymphoma, follicular lymphoma. Not only can these be classified by B cells, T cells, and other markers, but they can also be diagnosed by finding the translocation. And even a Ewing sarcoma, which technically, I guess we could probably put that in the same category of a hematologic malignancy, okay? More or less, loosely speaking. So, let's get back to a couple things we mentioned already. We all have seen all of these multiple steps contributing towards the development of a malignancy, not only in causing the malignancy, but promoting it, and things like making it grow, making it metastasize. This is a chart that I never really liked very much, but sometimes, and certainly in some of the textbooks, they'll talk about the concepts of gatekeepers and caretakers. Now, if we know that we have DNA repair genes which repair defective DNA, which could cause the mutations, you could call the family of DNA repair genes caretakers. But then there are gatekeepers as well. Okay, so if you look at this concept of oncogene or a tumor suppressing gene, we are not really talking about a gene which suppresses a tumor, but a gene which suppresses somewhere in the stage of progression of a tumor. We call these the gatekeepers, okay? Now, the concept of both of these things are actually in the concept of, let's say, initiating the malignancy when these things go wrong. But then we have something called tumor progression. How does the tumor progress? Well, we saw that it can draw in blood vessels. We can also see that that tumor can progress by differentiating further from its original malignant cell into more differentiated cells, many of which, of course, may not even have the capacity to multiply anymore, and many of which could very easily undergo apoptosis as well. So, in my opinion, this is the single most important slide in understanding what causes cancer. Well, what causes cancer are mutations. You already know that. We know what causes mutations. We always call them the usual suspects. They're the same groups of things which cause birth defects, which cause genetic mutations, which cause inflammation, and we call them in generally the category of physical, chemical, and pathogenic, bacterial, viral. Okay, these are the carcinogens, the specific carcinogens involved in the actual initiation or the malignant transformation that causes the cancer. But if the cancer is caused, you have to understand that there's another group of factors which are called the promoters. They don't cause the cancer, but once the cancer is caused, they cause the cancer to grow, to promote. I think a very good general term for a promoter would be a hyperplastic agent. Many hormones are hyperplastic agents, but there are other factors in the promotion of a malignancy which has already been initiated by carcinogens to make that tumor promote, to grow, to become bigger. Let's talk about it some more. Here's your carcinogen. You can have detoxification of it and excretion, right? Or you could have metabolic activation by being indirectly, you could have your metabolism make it more carcinogenic. Or it could be non-carcinogenic and it could be metabolized to be carcinogenic. In that case, it could also be excreted as well. But if it's not, it binds to your DNA and it damages your DNA. But guess what? If you have DNA repair genes, it's fixed. If your DNA repair genes are mutated, they could progress. Okay, and don't forget, not only can DNA repair the nucleic acid, repair the cell, but the cell can also die. But let's say the DNA can't be repaired. Now you have a permanent lesion that's going to be continued in future generations. And what determines the proliferation, the growth, the multiplication, the mitoses of those cells? That's the concept of promotion. So not only have you technically a malignant cell here, technically clonal cell, technically one cell, but now you have these factors which promote it, which multiply it. So here, let's make this very, very simple. For all cancers, you need two factors. You need the actual carcinogen, the agent which causes the malignant cell, and you need something to promote it, to multiply it, to make it grow. And we're going to go into that even more. Who are the usual suspects? Who are the initiators? Who are the carcinogens? Okay, well, it's the same people, the same bad guys that are associated with causing inflammation, birth defects, immune suppressions of cells, or mutations of anything. The same suspects that cause most of human diseases are in three categories: chemicals, radiation, which we can call physical, okay, or infectious pathogens. Here's a list of the common, well-known chemical carcinogens, the initiators, okay? They can cause cancer by virtue of having a direct influence on cells, these chemicals themselves, or they could be metabolized as procarcinogens to be direct. For example, did you know that the polycyclic aromatic hydrocarbons, cigarette smoke, okay, that they are not in themselves direct carcinogens, they're metabolized to become carcinogens. The so-called azo dyes, the aromatic amines, same thing. Things from plants and foods, like, for example, aflatoxin B1 from fungi causing hepatomas. They don't do it directly, they're metabolized. Or griseofulvin, which was something that was another antifungal, can be metabolized to be a carcinogen, an initiator. If you don't know what a cycad is, I didn't know what it was. It's this, and it's a natural compound, and there's something that can be found in it called, hold on, let me drop this guy down here. Oh, what happened? Oh, let's do it manually. Psych acid, that's a carcinogen that could be converted directly from being a procarcinogen. Saffron, okay, that's also technically a carcinogen. Betel nuts, we know people that chew betel nuts. I think it's very common in certain places like India and other places, but technically that's associated, like cigarette smoke, with a high incidence of oral cancer. That's also a procarcinogen. But these various chemical compounds, and I can't say I know exactly where they are all commonly used, but these are the chemical structures. The propiolactones, the DMSO, dimethyl sulfate, the diepoxybutane rings, even anti-cancer or chemotherapy, the cyclophosphamide. Isn't that something? The chlorambucils, the nitrosoureas, they react to kill cancer cells. Isn't that the purpose of an anti-cancer drug? But in themselves, they're also carcinogenic. Chew on that for a while. Something called an acylating agent. I'm not very big on chemistry, but there is the acetyl imidazole compound, or the dimethyl carbamyl chloride. These are all common, well-known carcinogens. Government knows about them. They are banned or protected, if they are stored in toxic waste dumps. And they basically represent things that are well known. It's the things that we don't know are well known. Or here, let's go a little further. There's the things that are known as carcinogens, but the evidence is hidden by, let's say, big pharma or big corporations, like the cigarette smoke carcinogenic properties were hidden for generations. That's still going on, folks. That's the nature of big corporations. They don't care about your life. Okay? Other common, less complicated carcinogens, the nitrosamines, okay, those are in tar, those are also in nitrites. Vinyl chloride, there was a big factory in Kentucky that used a lot of vinyl chloride. A lot of their employees were coming down with malignancies of blood vessels, angiosarcomas. The heavy metal, nickel, chromium, many insecticides, fungicides, and of course the polychlorinated biphenyls. We know the PCBs. Okay, if you want to see the chemical structure, this family of compounds are also known as direct initiators as well. So that's what causes cancer, folks. But what about the promoters now? Now that the cancer is caused, what are the things that make the cells grow, make the cells invade, make the cells multiply? Well, commonly many hormones do, The same hormones which go to nourish cells in your body to make them grow, to make them multiply, technically are promoters if the type of tumor is receptive to them as well, okay? Compounds like the 4-bol esters, they activate kinase C, and that itself causes cells to promote, to grow. Same thing with phenols. Any drug that can be listed or studied as having an effect on the growth of cells, whether they're cancer or not, could be regarded as a promoter for chemical carcinogenesis. Okay, I almost feel like making you stand up now, but I won't. If I was in a classroom, I would order you all to stand up and repeat after me, because this is such an important concept, and unfortunately, even many, many physicians don't know it. You need both initiators and promoters to develop and spread cancer. You want me to say it again? I hope you can say it again out loud. You need both initiators and promoters to cause and spread cancer. Okay, radiation. That was one of the initiators. We know that ultraviolet radiation, regular old sunlight, is a huge, huge factor in all three of the common skin cancers: the basal cell carcinoma, the squamous cell carcinoma, and the malignant melanoma. Technically, any type of ionizing radiation, radiation which produces ions, whether it's particulate radiation, things that have mass, or whether it's simply electromagnetic photons, that's technically causing mutations as well, doesn't it? Obviously, you ionize something, has an effect on the DNA. In particular, the ionizing radiation seen in Fallout in Japan caused like a huge amount at first of the hematopoietic malignancies, the leukemias, the lymphomas, and then after a period of time, even the non-hematopoietic, like thyroid, okay, due to the fact that a thyroid takes up I-131 because it thinks it's non-radioactive iodine. Solid tumors are a little bit less susceptible for radiation carcinogens, but once again, we're seeing more and more examples of it. So the general category of cancers which are strongly linked to radiation are the leukemias and the lymphomas. You can see a basal cell carcinoma in somebody that has not been exposed to much starlight, but if they've been exposed to therapeutic radiation, they can get a basal cell. Viral carcinogenesis. We know that the virus, the human papilloma virus, is not only a cause of many of the benign squamous proliferations of the skin, but the downright squamous cell carcinomas as well. Epstein-Barr virus in the herpes family, very strongly linked in the development of Burkitt's lymphoma. Now, hepatitis B virus, it does not directly cause hepatomas, but it's one of the most common cause of cirrhosis worldwide, Asia, Africa, and hepatomas develop almost always within the liver that's already cirrhotic. So all of those nodules in the cirrhosis, which are constantly being generated, are more susceptible to proliferate when they're exposed to, after they've been caused by hepatitis B virus. It's kind of an indirect link. Do you remember this virus called HIV? HIV used to be called HTLV3. Before we had HTLV3, we had something called HTLV1. And that virus, also a retrovirus, because, it's in the AIDS family, was the cause of T-cell malignancies, leukemias, lymphomas. And finally, patients that have immunosuppression have tumors, low-grade malignant sarcomas due to a virus also in the herpes family, Kaposi sarcoma human virus, which is called HHV, or human herpes virus 8. Okay, these are all strong viral links. How about the bacteria? Whoops, I'm sorry. The bacteria, there's a bacteria called H. pylori. It's basically the cause of most ulcers, duodenal, gastric, but it is also linked to almost all of the gastric lymphomas, what they call the maltomas, because it's a malignancy or lymphoma of the mucosal associated lymphoid tissue of the stomach. Now, if that wasn't enough, and if you can believe me, that H. pylori is also considered as a strong causative factor in the actual carcinomas, the adenocarcinomas of the stomach as well. Okay, we'll take another sort of a deep breath, because we know that tumor cells don't have all the surface antigens as normal cells. They may have new ones, they may have a loss of cells, and they are susceptible technically by immune surveillance. You know, they could be not recognized by natural killer cells, T cells, the various types. They can be swallowed up by macrophages for not fitting into that nice little MHC profile. Or they could be attacked by antibodies. So these are your general ammunition, your immunity against tumor cells. Normally, cells have all of the proper MHC molecules, the class 1, where they're going to be left alone by your T cell recognition, the T8s, perhaps the natural killer cells. However, tumor cells can have an oncogene making an oncoprotein, which is not recognized. Or it could have a self-inherent protein that is now mutated. Okay? Or you could have an overexpressed protein, okay, which is now recognized by your immune system. In every case, these are T cells, okay? Or you could have an oncogenic virus, which is not fit in nicely to your MHC recognition, and that could be attacked as well. So that's the general scheme. Now, I don't know if you remember this from the last webinar. I should probably show you a picture again, but let me make this very simple. Let's say you're looking at two tumors under a microscope. One of them hardly has any lymphocytes at all as part of the tumor. The other one is loaded with lymphocytes. Maybe there's more lymphocytes than there are tumor cells. So the question is, and I think you know the answer, you don't have to type it in. If you see a tumor that is abundantly surrounded by lymphocytes, all you know from the microscope is that they're lymphocytes. You don't know if they're T cells, B cells, natural killer cells. The ones that are going to do better are the ones where you could see that there's going a lot of immune defensive going around. So the more lymphocytes you see in the tumor, generally speaking, everything else being equal, the better the patient's going to do. Nobody else will tell you that except me. So how do the tumor cells now escape immune surveillance if they have all these possible weak areas that make them susceptible to, let's say, the T cells? Well, they can mutate, okay? And in the process of mutation, they lose those antigenic sites. Or they could have a decreased in the MHC1 molecules on the surface cell itself, okay? Having an abundant amount of normal MHC1 molecules keeps that cell protected, but they could have reduced. And remember, it's not just an antigen hooking onto an antibody or vice versa, okay? There are other molecules involved in recognition, and some of them are called, or the general name for them are co-stimulation molecules. They could have a lack of co-stimulation molecules, even though they might have an abnormal antigen that's recognized by an antibody. The immunosuppressive agents, that's one of the things they do, is they suppress your immune response. Or they could have the antigens present on their surface and ready to be attacked, but there are mechanisms by which the antigens can be hidden or masked. just like bacteria and viruses can do. Now, this is the most spectacular one of all at the bottom. What if the tumor cell avoids apoptosis, not only by mechanisms of not being recognized by the apoptotic process, but what if the tumor cell itself swallows up and kills the T cell? Imagine that. There are certain tumors, they're mostly in the macrophage family, but that actually can kill the body's immune cells that are trying to attack them. That's seen rather rarely, but it's a well-known fact. This one is so obvious I almost don't have to show it. There's your host. The tumor can encroach on any organ above, below, and back and front, lateral to it, obviously. The tumor can also produce hormones or hormone-like substances. The tumor, by virtue of invading mucosal membranes or blood vessels, can cause bleeding or infection. Okay, the tumor can involve vessels to where there's actually infarction of where that vessel leads to, and obviously the tumor can metastasize as well. So these are all things that tumors do to cause problems, to cause serious problems, to cause death. And it's really nice because you could probably think of this, all of these concepts of being relatively anatomic in nature. Okay, there's a wide variety of non-anatomic mechanisms, okay, that a tumor has that can kill you and make you very, very sick. Cachexia. Why do patients with malignancies waste away? Well, if you're normally on a diet, technically, you're going to lose more fat than muscle. But if you're losing weight because of a malignancy, you're probably losing almost just as much muscle or non-fat as you are fat. Okay. Furthermore, in malignancies, macrophages can release a substance. It's called TNF. And remember, TNF alpha is one of the growth factors. It's one of the cytokines. That's an extreme regulator of the other cytokines. So if your tumor causes production of TNF alpha, that's going to be causing the macrophages to chew up everything. That's another reason for cachexia. Same thing with interleukin 6 can stimulate or produce by tumor cells. Another thing that's also made by tumor cells is a compound, which I really don't have too much more information on, called PIF, but its name would indicate what it's doing. Proteolysis inducing factor, which means it's going to be lysing proteins, which means you're going to be losing protein, which means you're going to be losing tissue, which means you're going to be losing weight, which means you can be very, very theoretically wasted away or cachectic. It wouldn't be fair if we didn't mention the paraneoplastic syndromes. A paraneoplastic syndrome is a syndrome which is not directly caused theoretically by the anatomic or effects of a tumor, but it's so highly linked to it that when you see a patient with a paraneoplastic syndrome, you can suspect that there's a malignancy going on, and even malignancy in a certain place. The greatest family of paraneoplastic syndromes are the endocrine paraneoplastic syndromes. If it looks like there's an overproduction of a hormone producing a endocrine syndrome, it might not be the actual endocrine gland that's producing the hormone. It could be a tumor cell. I'm going to give you a lot of examples of those. In myasthenia is often seen in patients with lung cancer. Okay, and if you see a patient with myasthenia, muscle weakness, okay, you might suspect that maybe there may be a cancer, and specifically lung cancer is the most common one associated with it. That doesn't mean it's there for sure, but it's highly associated. If you remember when we didn't talk about diabetes yet, but there's a common skin condition in diabetics, usually in the creases of their neck or of their armpits, called acanthosis nigricans. Nigricans means it's pigmented. Acanthosis means the epidermis is thickened. And also dermatomyositis, or inflammation of skeletal muscle. These are associated with malignancies as well. Here's the acanthosis nigricans. This is something called HPOA, hypertrophic pulmonary osteoarthropathy. It's like an arthritis. Look at the thickening of the terminal portions of those fingers, okay? Oh, let's see, how do I get that back? There we go. When you see that in a patient, for no obvious reason, one of the things you can consider is that it may be associated with the lung cancer. Patients that have coagulation problems, okay, or thrombosis, venous thrombosis, a Trousseau syndrome, or patients that have venous thrombosis, and it may be migratory, often associated with malignancies. I think it was first described in pancreas and GI, and that's the common places where you might see a migratory thrombophlebitis. Endocarditis as well, okay? Hematologic. Almost every patient, I can guarantee you that if you went into the hospital now and looked at every patient that had an advanced malignancy, they're probably anemic as well. That's very, very, very common and very, very nonspecific. Something else is that there are a multitude of reasons why a patient can have a nephrotic syndrome. Basically, the underlying thing is a damage to their glomerular basement membrane, so they're leaking out all their proteins, okay, and because of that, they're also very edematous, and they have tons of protein in their urine and decrease of protein in their blood. One of the things it's associated with are a pretty wide variety of different malignancies. So these are the paraneoplastic syndromes. I'm going to give you a laundry list here, a big one of the endocrine. Don't freak out, but there's a good number of them, and here they are. Overproduction of ACTH could produce a Cushing-like syndrome. The most common thing would be a small cell carcinoma of lung, but also in pancreatic carcinomas. Okay, if you have, for example, a tumor which is expressing a lot of antidiuretic hormones, or something similar called atrial natriuretic hormones, that is often seen in small cell carcinoma of the lung, the syndrome of inappropriate ADH. Okay? Squamous cell carcinoma of the lungs can secrete parathyroid or parathyroid-like hormones. Very often these ectopic hormones that are secreted by tumor cells are not exact chemically to the normal hormones. They might be a little bit different chemically, but they could have the same effect, okay? So not only with cancer of the lung, but breast cancer, kidney cancer, lymphomas, ovarian, might have a situation in which they are hypercalcemic due to ectopic production of parathyroid or parathyroid-like hormone. Certain sarcomas, okay, and liver cancers can secrete an insulin-like substance, so they would be hypoglycemic, okay. Patients with bronchial adenomas, certain pancreas cancer, but bronchial carcinoids, or carcinoids of the GI tract, might result in the secretion of a lot of a serotonin. And remember, we said serotonin is a very, very powerful vasodilator, so they could be flushed, and they can also have symptoms of diarrhea as well. polycythemia. Let's say that you have a renal cancer or a cerebellar type of vascular tumor, or even a hepatoma producing an erythropoietin-like substance. Well, then their hemoglobin and hematocrit is going to be increased, aren't they? And they'll be polycythemic. Grading and staging. Pathologists spend a large portion of their day describing and talking about tumor cells, and we went over thoroughly that if the tumor cells look a lot like the normal cells, we call it a well differentiated. If they don't look like the cells they came from, we say poorly differentiated. You could give them numbers, you could use different adjectives, you could say good, bad, okay. And that will generally help you determine the prognosis. But something that's much more important than grading, which the pathologist does, is the staging, which might be the job of the radiologist or surgeon or the pathologist working together. It's much more important how much a tumor has spread rather than how bad they look like under the microscope. So in many systems of the body, they have the TNM classification. T stands for tumor. You could put numbers after it depending on how big it is. N is for lymph nodes, as to how many are involved, how big are involved, where they're involved. Or M, you could put numbers after the N, you could put numbers after the M, which means the presence or absence of metastases. So you got to understand, and I think it should be obvious, that staging tells you a lot more powerful information about that patient's prognosis than grading. But grading is important too, okay? What is this? Well, on the right, you could tell it's skin, can't you? You can see a stratum corneum, you can see a couple melanocytes, you can see acanthocytes, you can see a stratum lucidum. Just normal differentiation of skin. Now, you could see here, it kind of looks like squamous cells again. You could see some little bridges. Up here, you can actually see a pearl, so that's a well-differentiated. Maybe these are kind of like moderately differentiated. And down here, they look poorly differentiated because they don't even look like squamous cells anymore. So this is classical adjectives or descriptions of whether a certain type of cancer, a squamous cell carcinoma, is well, moderate, or poorly differentiated. Well usually means you see pearls. Moderately means you can see these little tonofibrils or desmosomes, which you see in the stratum spinosum here in the skin, which is the majority of the thickness of the skin. And poor means it doesn't look like squamous at all. So poor are easy to diagnose, but they don't behave well. And well are hard to diagnose because they might look like the normal tissue, but they behave well. Okay. And here, this is something we could have fun with. This, you could tell that these are all little glandular structures. This is an adenocarcinoma. It could be adenocarcinoma of any organ that's glandular. Could it be a breast? Could it be a pancreas? Could it be a prostate? Well, in this case, it happens to be a prostate, but it's just an adenocarcinoma. Now, if a normal prostate, for example, looks like this, okay, you can see secretion, you can see the nuclei at the base, you can see that the glands are all separated from each other by a little bit of connective tissue. If this is a normal glandular structure of a prostate, then take a look at these pictures here, and here, and here, and here, and ask yourself, which one of these pictures looks the most like normal prostate? Maybe it's this one down here. And which one looks the least like here? You can barely even recognize these as glands. And these are kind of intermediate. Well, you could actually put numbers on these, and this is called the Gleason system, where if it looks almost like normal, you call it a 1. If it looks so horribly bad it doesn't even look like glands anymore, you call that a 5. And then you can do that in another area of the tumor and wind up with a normal Gleason score. And that number, the urologists and the surgeons and the patients, they rely on that number. They want all their patients to have cancers which have low Gleason score, of which the best one would be a 2, and probably the worst one would be a 10, technically, because you're adding up 2 areas together. You diagnose cancer generally with a biopsy or a tiny biopsy through a fine needle, or even by just scraping the surface. So we all know that we diagnose or confirm malignancies, even if an x-ray or a physical exam or an MRI or blood tests basically are very, very, very strongly pointing to the fact that there's a malignancy. It generally has to be confirmed by people like me. And that's what I did in my whole life. And not so much now, but that's how you diagnose cancer. The things that we're going to be looking at in lab. Our third session will be entirely lab again, looking at tumors. Sometimes, even though we'll be looking at mostly at tumors that are stained with hematoxylin and eosin, we'll say the nucleus is blue and the cytoplasm is pink. A lot of times you can actually extremely help that by actually labeling chemicals, colored chemicals or chromogens to certain antigens or portions of the cell. So if you have like a very undifferentiated tumor, you might not even know whether it's squamous cell, whether it's an adeno, whether it's a sarcoma. But if you take certain antigens that those areas are supposed to have, it could help you better to categorize very undifferentiated tumors. It's also helpful in the classification of leukemias and lymphomas. I mean, if you just look at a lymphocyte under a microscope, you have to call it a lymphocyte. But if you know it's a T cell or a B cell or a macrophage on the basis of having stains which are specific for those kinds of cells, it's often used in the diagnosis of hematopoietic or hematologic malignancies. Let's say you have an adenocarcinoma metastatic to the skin or the lung or the liver, and you don't know where the hell it came from. Well, if you have a stain that shows that there were pancreatic antigens on it, or lung antigens, or colon antigens, then you know where it came from. And sometimes that's very, very helpful. And of course, sometimes in immunohistochemistry, or what they call IHC, I should have made these in red. In fact, let's make them in red. There's your I, there's your H, and there's your C. If you can tell that they have receptors for either estrogen or progesterone, that will help to tell you how well that patient will respond as a prognosis, and also whether those tumor cells, if they have receptors for estrogen, maybe you should try to use anti-estrogen types of chemotherapy, for example. We're almost at the end. There's a growing wide variety of tumor markers. For example, in a paraneoplastic endocrine syndrome, you can use the presence of the hormone level as being not only important in how much hormone the tumor is producing, but you could actually stain the tumor to see if it has those hormones present. And that's more true with proteins rather than hormones, but some hormones are proteins. Oncofetal antigens like alpha-fetoprotein, the original carcinoembryonic antigen present in many of the adenocarcinomas, can help you tell whether a tumor is differentiated enough to be making these compounds, or if the blood levels are high enough, It'll tell you, for example, maybe there's a reoccurrence, for example. So if a patient has a very low level of PSA after he gets his prostate cancer taken out, but then all of a sudden it rises, and without necessarily seeing a resurgence of the tumor, you know that that's a bad prognostic feature. Many of the tumor markers are glycoproteins like CA125 and ovary. And of course now, with the ways we have massively improved our genetic inquiries, or actually measure genes or mutations of the genes, like P53 and RAS. There's a wide variety of literature and studies that now show whether the presence or absence of a certain gene is a good or a bad prognosis. We're almost done, which is good because there's only 4 more minutes on the clock. I made this little slide myself. And this is kind of interesting. What we're going to be seeing in regular pathology lab are slides, and they're going to look kind of pinkish blue, and we're going to see how the cells are basically growing, or present or absent. If we wanted to stain those cells with kind of a brownish stain to see if they have certain antigens, it'll help us better identify the cells. This is a classical immunohistochemistry slide, or immunoperoxidase is an older term. If you have a method, however, to look at the patient's genes, which determine these antigens, and ultimately not only determine the structure, but determine everything in that patient's genome, the presence or absence of a gene or a mutation of a gene, you can see by virtue of doing arrays. So a lot of the pathologists are saying, we're not going to have to look at microscopes anymore, or we're not going to have to look at all these special stains. Maybe in the future we'll just be looking at the presence or absence of genes or their mutations, like in a genetic microscopic array, which you see down here. We're done. Thank you for being with me through this very intense session. Let's see if we could get back to look at the ugly man again. I once again wanted to tell you that for me, and maybe probably for you, this has been a very intense webinar. Last one was fun. Second one was intense. I feel like I'm kind of knocked out, and maybe you do too, or maybe you left. But the third one will be a lab, and the labs are always fun. So we're going to be doing some fun, good things, looking through the microscope in 5 days from now, next Tuesday. And up until then, you know what I'm going to say. I'm going to say rock on buzzards, and I'm going to play for you our very last song. Well, you know what we say now. I hope you enjoyed that picture I took outside of my house. I got a red tree, a yellow tree, and a green tree all right in front of my patio. So there's my little cutoff button. And here is my other cutoff button. You know what we do now. We say, rock on, buzzards.